Hello, everybody. Welcome to the Department of Electronic and Electrical Engineering Spring into STEM lecture, hosted by Dan Mannion. We're just going to wait a couple of minutes whilst everybody joins us, and then we will pass straight on to Dan. Okay, Dan, I think you're good to start now.
Okay, thank you very much, Navta. So yes, welcome to Making Siri More Like Us, one of the Spring into STEM sessions. So today is all about a field that I research called Neuromorphic Engineering. And it's something which a lot of us might not have heard of before. And that's okay, because hopefully by the end of the talk, we're going to have a better understanding of what neuromorphic engineering actually is. But most importantly, why it's needed. Because fortunately, neuromorphic engineering relates to a topic which I'm sure many of us have heard of, and that's machine learning. Because although sometimes it might seem that machine learning has sort of outperforms us in many tasks, actually, machine learning can learn a lot and has to take a lot of inspiration from yourself if it wants to be more ubiquitous and scalable in the modern world. But before we get to that, I just want to go back to the beginning and have a shared understanding of where machine learning is in this current day and age. Then we'll look at some of the problems it faces. And then finally, I'll present neuromorphic engineering as a solution to that. So we might as well go back to the beginning and look at a nice project which gives you a good example of where machine learning is. And that's with Google's AlphaGo. So some of you would have heard of this before because it was a fantastically successful project. Essentially, Google started a project to create a machine learning entity that can play Go, a game where you try and surround your enemy pieces, and that's shown in the bottom here of the screen. So it's a really interesting game to pick because it's both technically challenging, but also requires an amount of creativity. And the AlphaGo went on to beat grandmasters in the game and was a feature of this documentary. What's interesting, though, is that at the beginning, it took inspiration from human players. But following the successes of AlphaGo, Google decided, actually, no, humans weren't needed. And they moved on to a project called AlphaZero. And AlphaZero removed all forms of human inspiration in a way, in that it, rather than learning from human versus human games, it just played against itself. And initially it was very bad, but as it gets better and better, its performance increases, as we can see in this graph in the bottom, and eventually gets to the level of beating grandmasters. So from this, from the perspective of these successes, sometimes we can be made to feel that, okay, we should probably give up. Machine learning's beaten us. But what's really important to remember is that what we see from these examples are the successes. What we don't see is how those successes are achieved or attained. And that's important because in this kind of challenge or problem, hardware, which is what the software is running on, plays a really important role. And you could consider it as an analogy to doping in professional sports. The more computers I give to the problem, the more power I inject in, the more searches that machine learning entity can do. What do I mean by search? Well, imagine you're playing chess. You can ask yourself the question, if I make this move, do I give myself an opponent an advantage? And I can then go one step further and say, having made that move, if I then make this move, do I give myself an advantage? And if you keep repeatedly asking yourself these questions and these queries, you build up with a branch-like representation of the game. Now, as a human, I can only store so many of those queries, a branch of a certain size, let's say. But for a computer, as we chuck more and more hardware and more power into the system, it can carry out more of those searches within a given time and store the results of them. So clearly it gives a significant advantage as we have more hardware. And we see that in the data. So if we look at the hardware of AlphaGo, which is summarized in this table, we can see that CPUs and GPUs, which we'll use to quantify the amount of hardware, when it's in a low number, 50 to 60 units, we have this is the score of how well ELO plays, and it's an average score. Now, we don't get to the grandmaster level until we enter into a distributed system, which is shown down here, when we start having hundreds and thousands of computational units. So clearly hardware is playing a role. So the image of one human versus one computer is a bit misleading. Another performance metric we can consider then is the power consumption. So how much power does a human consume compared to the computer? Well, a rough approximation for a human is that your brain at rest consumes around 20 watts. So if we remember that figure, 20 watts, we can then ask ourselves, well, how much is AlphaGo consuming? Well, in the game against Fan Louis, which is seen here, he's consuming his 20 watts, as we saw earlier, probably slightly higher. And 20 watts in context is about the same amount as, or slightly more, sorry, than a low energy light bulb. Whereas AlphaGo, in comparison, was consuming approximately a megawatt, so 1,000,000 watts. So clearly there's an asymmetry there, and there's some challenges which we need to overcome. And it's another point that we should remember, that these kind of images of one person against a computer can be quite misleading. So this is a bit more representative of the situation. So keep that in your mind. Of course, we're also, this kind of effect and inefficiency affects us at a much more personal, closer level. And that comes in the form of our mobile phones. So most people would assume that Siri's work is carried out on the phone, but that's only partly true. When Siri's in a low power mode listening for those two trigger words, hey Siri, even it has some machine learning analyzing the text, but even when it thinks you said it, it's not entirely sure. It still has to send that to a server and receive it back in order to be entirely confident. And the reason for that, as you probably guessed, is because it simply consumes too much power to be running intensive machine learning tasks on something like your mobile phone. So although these are quite local problems and specific, it turns out that power consumption in machine learning is also a more global issue. So in this study, the researchers analyzed the amount of CO2 produced for machine learning, a particular kind of machine learning network, a neural network, not just when it's used, but throughout the whole of its development cycle. And they found that the development of that neural network produced about the same CO2 as 7 years of an average human life. So clearly, this is an issue. Machine learning computational approaches are struggling with power consumption. And if we want to make them better, it's something we really need to tackle, especially if we want machine learning to exist in all of our electronics, in our phones, kettles, and ovens. So first off, what's causing this issue? What is the problem? And the problem is based in how computers compute, how they're designed and how they're built. Because the majority of computers, your CPU, for example, operates with an architecture called the von Neumann architecture. In that architecture, there is a separation between where the processing is done and where you store data. So when you want to do a computation, you have to read data from memory into the processor, do your maths, and then save it and write it back into memory. And that works perfectly fine. The only problem is in this exchanging of information between the memory and the processor. If that's slow, then you end up limiting your system and you have a bottleneck, which we refer to as the von Neumann bottleneck because it's inherent of that architecture. Now, the problem is that machine learning relies on mathematical operators that do this toing and froing of data quite intensely. And this bottleneck then, therefore, limits machine learning processes, and so you have to have more operating in parallel. And a real concern is that this bottleneck isn't getting any better. So if we look at the computational rate of a CPU, which is what we're looking at here, we're looking at the performance of a CPU, so how fast it can compute, and then the performance of memory, and that's in terms of read-write speeds. And what we see is, over the years, a gap forming. This graph is up to the year 2000, this graph is up to year 2010. Now, although there's a slight tapering off, so suggesting the situation is getting better, that bottleneck is going to have less of an effect, it's still not fully closed, that gap. So we need to find a way of getting around that, because at the moment, the architecture is always going to be limited. And the solution to that can actually be found in when we look back to AlphaGo. So what we're seeing here then is the power consumption of AlphaGo in various different forms. First, against the game we saw earlier, where it was consuming almost a megawatt, and that was a fan with Fan Louis. But then, interestingly, we see a very significant reduction in power consumption when AlphaGo plays against Lee Sedol, and that reduction continued further into its alpha zero. So the question is, how on earth did they do that? And the answer is hardware, and it's revealed in the bottom here, in how they moved from using GPUs to hardware called a TPU, which is shown up here. Now, TPU is very similar to a GPU, except it's designed specifically for carrying out those computations we mentioned earlier, which machine learning is so heavily dependent on, and which is inefficient in the von Neumann bottleneck. So what we're seeing is a general trend from general computing hardware, like a CPU, to more application-specific hardware, such as the TPU. And that shouldn't come to a surprise, because it's nothing new. It's exactly the same reason why a GPU was developed, in that CPUs were not suited for performing graphics-based calculations. So we need to move from generalized computing to developing application-specific accelerators. And the TPU is one approach. The approach that I'm going to introduce you today that I'll introduce you to today is my field, which that I work in, and that's the one called neuromorphic engineering. So neuromorphic engineering takes the approach of looking at your 20 watts, your brain consuming at 20 watts, and realizing, okay, we need to replicate this. We want to be inspired by this. So we look at how the brain computes and then try and copy it. So in order to do that, we need to have a basic model of how the brain carries out computations. And the model we use is a very highly abstracted model, because it's a very complex system. We assume the brain consists of neurons, connections between those neurons called synapses, and axons, which allow the propagation of signals from one neuron to the other. So what we can see here is some artificially grown neurons on a substrate. This big bulbous shape is the neuron with an axon, and then all of the mesh around the outside are dendrites, and there'll be synaptic connections between the two. So with this structure, then, we're going to take the bio-inspired approach. Now, some of you who do machine learning will probably be saying that, hold on, this looks very similar to what we're used to. Neurons, connections, called synapses, and then weights. The key difference then in these kind of networks that we build is how information is encoded. So in biology, information is not encoded in continuous numbers from, say, 0 to 255, like a neural network would, but instead it's encoded in spikes. So a neuron will produce a spike, and that spike can change in a number of different ways. The shape of it can be changed, the amplitude of it can be changed, and the frequency with which spikes are produced can also be changed. So what we have here is a capture of some biological data of a neuron actually producing spikes. And we can see a wide range of frequencies, from none at all to a few spikes to almost like a burst of them. So the first thing we have to do then, in neuromorphic engineering, is we need to be able to replicate this spiking behavior. And that's been a research topic right from the onset of this research, of this field. So here, for example, is how we would reconstruct a neuron using standard CMOS electronics and transistors. The only thing is they're using a slightly different regime. So this is the circuit. We won't go into details. And this is the output that it produces. And what we can see when we compare this to what we were seeing in biology is we're getting really good replication in terms of the form and the dynamics of those biological signals. Each one of these is achieved by changing very slightly the biases inside this circuit. It's all the same circuit, but we're able to control its responses. So that's great. We have really good dynamics in the neurons, but we still have the second part of the system. We still need to be able to build those synapses, which are really important. So what is a synapse? So I said earlier, a synapse is the connection between two neurons. Key thing though, is that it's not an ideal connection. When the spike crosses from one through the synapse, it's actually processed in some way or transformed. And in the simplest sense, we can assume an attenuation, which we can call the weighting. And the way this weighting isn't static, okay? This weighting changes with time in response to stimuli and how neurons fire. So it's commonly accepted that it's in how these synapse, the weights of these synapse changes, that is how learning is achieved. So there's a lot of different rules or protocols that these synapses have experimentally been shown to follow. We won't
3 minutes left, Dan.
Cheers, thank you. We won't go into the detail, but essentially we try and replicate their responses by using a device which we research in our topic, in our group, which is Memristors. Memristors are very simple, metal, insulator metal, and we can get them to replicate the learning patterns we saw in the synapses with this very simple device. And that's really advantageous because it means we can use lots of them, which is what we need for neuromorphic engineering. So we have our neurons, we have our synapses. Can we build those big networks that can compute things? Fortunately, the answer is yes. So there's a lot of different examples of neuromorphic chips. And here, these aren't all of them, but here we have some of the big names in the fabrication industry, IBM, IMEC, Intel. And they've done some really cool studies to investigate how these work. So True North had their neuromorphic chip, and they tasked it with labeling images and word spotting. So an image, is it a cat, a dog? Word spotting, are you saying, hey Siri? And they found that it could operate on the milliwatt scale, so less than the human brain, and a very high rate of 2,600 images per second. So it clearly works, but the question is, does that low power, is it a compromise? Has the performance dropped, which is what we might expect? And when we look at table 3, which is a summary of how well it performed on a number of different data sets, it looked like it hasn't actually dropped in accuracy that much, roughly 1 to 0.5% drop in accuracy, which is really, really beneficial, because what it's showing us is that we can get state-of-the-art performance at low power if we go neuromorphic. Another nice example of that is Intel's Loihi chip. They ran inference experiments on their chip and found that they could perform with 100 times better power consumption per inference than, for example, a GPU. Of course, as a field, we face challenges. Those challenges, which is what I'll use to just summarize up the talk, to bring the talk to a close. So first challenge we face is converting networks. Industry research has been heavily driven on deep neural nets, convolutional neural networks. So we need some way of converting those kind of networks into spiking neural networks. It is a topic studied and it's making progress, but that's one challenge we face. Also, learning rules play a very important role. So we need to develop new ones and understand how they interact in the biological systems and make sure they're not just a byproduct, for example. And then finally, the hardest one when it comes to developing neuromorphic hardware is reconfigurability. So the idea in that if you have a deep neural network, I can very easily change the number of inputs or add new neurons or add extra layers just by changing my code. On the other hand, if I have physically built hardware, it's much more harder, and I sometimes have limited resources. So there's some of the 3 challenges. Hopefully I've been able to summarize up what neuromorphic engineering is, but the key point really is why it's needed and the power consumption issue within some machine learning hardware. So thank you very much for listening. Just before we go to the Q&A, just want to say thank you to, acknowledge, the team that does this work at UCL. So we're based in the Electronic Engineering Department, and we're led by Tony Kenyon and Adnan Mohonic. And there's a whole group of us as research staff and PhDs working on the project. So thank you very much for listening. Hopefully that wasn't too much too quickly. If you have any questions, I think we'll open up now, if that's okay.
Yes, Dan, thank you for that, Dan. So very quickly, a question about whether this recording will be available later. Yes, it will be, and I will send that around once it is. So to your first question now, Dan, Is there a point of diminishing returns where adding more compute units doesn't yield a proportional gain in ELOs?
Yeah, so that question's addressing the AlphaGo's progress in the game of Go. I'm not an expert in that, so I have to be honest, I'd need to look into it. Clearly, that what we saw was we saw there was a level in the training, a plateau, which would suggest that it's not just a computational limit, but actually an algorithmic limit, in that no matter how much time you're given, it's still struggling to just get any higher. So from outside of that, it seems like, yes, there is a limit, but I'd suggest reading the research paper to be entirely sure. It's not my expertise. Hopefully that's answered your question.
Right, next question.
Yep.
Could neuromorphic computing be useful in consumer hardware? And when could this technology become mainstream?
Yeah, that's a really good question, and absolutely, that's where this kind of hardware is really where we've got our sights on, because what we're looking at is hardware which is, as we saw earlier, sometimes there may be a limitation in how we can change it. So we're looking for low-level, small circuits which do an individual task, and they keep learning but keep doing the same task. So if we can find applications which seem like, yes, that probably is consumer hardware, where we want low power and we want battery power. So yeah, definitely the area where neuromorphic engineering wants to end up in. In terms of when it will be within industry, I think it seems like it would be a 5-year, 10-year thing.
All right, next question. Can the findings of neuromorphic engineering be reverse applied to neuroscience?
Yeah, so a lot of people are involved in that part of neuromorphic engineering as well. So there's a really good there's a project called Spinnaker, which is based on spiking neural networks, but using more conventional computers, although also custom designed accelerators. And one of a big role of their project is doing that kind of reverse engineering, helping neuroscientists simulate arrays or matrices of spiking neural networks. So it definitely can be and is being applied, which is a really interesting part. Also, on that note, people often use these circuits to interact with biological neurons, because it's the kind of computer that it's, I suppose, most akin or similar to the way those neurons compute. So if a neuron is producing a spiking output, you could argue the best way to process that or interpret it is using a spiking neural network piece of hardware. Hopefully that's answered that one.
Okay, next question. This is from an A-level student. It's great to have you join us. Machine learning is new to me, and it was explained that a machine learns from its past experiences. From this, is it true that any given machine will not know what to do when it encounters a new problem it has not faced before?
Okay, so it kind of depends on that. So there's lots of different kind of neural networks, and it depends on the way the machine learning algorithm is built. Some approaches will be quite limited in the problem they're tackling. So you generally have some error function, which is the way you determine how good you're solving the problem. Okay, and if the error function goes to 0, great, you're performing really well. But as you start performing badly, then that error function increases, and your network has to be able to adapt and reduce that error. If you're doing if your algorithm is designed to be able to adapt to changes in environment, so that it so it can adapt the way it changes, then it could potentially tackle a new problem. But there are also limitations. If you have to start reading new data which you're not previously reading, then you're not going to be able to solve it. Also, if your error function is now poorly defined for that new problem, you're not going to be able to solve it. But I mean, a nice example of this question to show that it would actually be possible is when you look at AlphaZero, because AlphaZero, AlphaZero was designed to learn any game. So AlphaZero works on the basis that it won't be getting any assumptions about the game, but it'll just start playing against itself, and it will slowly learn the rules of that specific game. So that's kind of an example, I suppose, showing that it would be possible, as long as you have some very generalized assumptions that can be applied to a wide variety of problems, then it is possible, as shown by AlphaZero.
Okay, next question. Are the current neuromorphic chips powerful enough to perform similar levels of computation as the AlphaGo system? And if not, when do you think that they will be?
So so I'm answering this question off the top of my head. So if anyone in the chat wants to contest this and say they have a fantastic system, then I'll admit I'm completely wrong. But I don't think so. The success of AlphaGo and AlphaZero is state of the art. It is phenomenal. Neuromorphic engineering is still in its early phases, and we're dealing with, I suppose, smaller systems. So at the moment, I think not. And I honestly don't think I'd be able to give a good answer or an accurate answer of when that would be, because it seems that maybe neuromorphic is going in a different direction rather than high power, going in low power applications. So yeah, I think at the moment, no, maybe in the future, but I wouldn't want to give an estimation because it wouldn't be too accurate.
Okay, so I'm conscious of time. I'm just going to do a couple more questions, Dan, if that's okay.
Yep.
We may not be able to get through all of them, but I will pop my email address in the chat and you can send some more over to me. For now, I'll go on to the next question. Does the Blue Brain project also work on the basis of neuromorphology?
So the Blue Brain project is quite broad and is focused on neuroscience and a bit of computation. Sorry, I don't know enough about the Blue Brain project, but I know it does involve some neuromorphic research.
Thanks, Dan. Next question. Which resources or books would you recommend for an introduction or closer look at neuromorphic engineering and its application?
So there are some really good books which I could recommend. If you're looking for the electronics, there's a good book written where one of the authors is Giacomo Indeveri. And also you can go back to the founding, a book which started the field. What I can do is put a list together and link to them, and then we can probably send that out to attendees. Would that work, Navta?
Yeah, sure. That's absolutely fine, Dan.
Yeah, I'll put a list together, and we'll try and focus on some technical text, and then also maybe some non-technical blog articles for people who don't want to get into the circuit details.
Okay, so I will do the last question now, Dan.
Yep.
Do you see mainstream computing architecture becoming efficient enough to compete with neuromorphic computing?
It's definitely a potential. I mean, we saw with AlphaGo the massive reduction in power from moving from a GPU to a TPU in the AlphaGo architecture. So it doesn't seem like, I mean, it's certainly possible. And that is another stream of research which is going on alongside neuromorphic engineering, and we're both being inspired by each other. So it is one potential. One key thing, though, is that separation between processing and memory. In neuromorphic, the two are very tightly coupled, especially when you're using learning rules and synapses, which are using online learning rules. I think this is hard to implement in your classic von Neumann architecture, even if you start bringing the memory closer to the processor so you can reduce the read-write times. Fundamentally, it's still different. But you could design circuits which do implement that online learning. When you start doing that, and people have done that, but when you start doing that, then you have to start tackling scalability. CMOS circuits can be, they can take up space because you're dealing with transistors, and transistors are quite bulky. They have 3 terminals. Whereas if in the neuromorphic engineering, we might try and use more nano technology, kind of nano wires, memristors, as we saw, we might be able to get a higher packing density. But yeah, so it could be, we don't know, it's too early to say.
Okay, great. Thank you, Dan. So that's all the questions answered within the time that we had. I've popped my email address in the chat. Please feel free to send over any additional questions, and I will try to get Dan to answer these over the coming weeks. Dan, over to you for some final words.
Oh, yeah, well, so thank you very much, everyone, for coming to have a crash course in neuromorphic engineering. Hope you enjoyed it. Go out and enjoy the sun if you have it. Thank you very much, Navta, as well, for inviting me to do the talk. It's been really a great opportunity.
Lovely. Okay, thank you all.
Okay, bye.